Hi N9s, welcome to our second PowerPoint for Year 9 Science. Just fixing that up, so it's actually term 1 week 2. We're going to be looking at the atom today, and starting a little bit more depth into the atom. After last week we looked at the periodic table, and we're going to look a little bit more in depth at what the atom is itself. So starting off, I suppose, the question, what are atoms? You've probably heard that term thrown around a few times. What exactly is an atom? Well, basically, we start by saying that everything you've ever encountered in your life is made up of atoms. So atoms, we sometimes say, are the smallest building block of everything. Atoms are so small, they cannot be seen, even by the world's most powerful microscope. Optical microscope, we should say, so like a light microscope like we have at school. We can't see atoms with that. In order to see an atom, you would need a scanning tunnel electron microscope, or an STM. Now, I know that we've had the electron microscope at school sometimes, but that electron microscope would not be powerful enough to see atoms. You'd need a really high grade scanning tunnel microscope for that in order to see those. So, summarising there, atoms are the smallest building blocks of everything in life. Going a little bit further, how does the atom connect with the periodic table, which was what we were talking about last week? Well, when we look at the periodic table, we know there's 118 types of atoms, or elements. And 91 of those are found naturally on Earth, with 27 of those being made in the laboratory. Now, when we say that, for example, the periodic table, hydrogen here, that is technically an atom. So we're talking about a hydrogen atom, or a helium atom, okay, or a chlorine atom down here, or a potassium atom down here. These represent the atoms. Now, in order to get an element and have them on the periodic table, you need a group of the same atom, so a group of hydrogen atoms coming together to make the element hydrogen. Okay, I'm going to talk about that coming up in a little bit more information. First off, though, when we're talking about atoms sticking together, they can form two different structures. So to start with, when they form clusters together, so for example, you've got a water molecule here, so hydrogen and oxygen, two hydrogens and an oxygen. These are molecules. When they form in a cluster like this, atoms form together or stick together in a cluster, that's called a molecule. But when they form grid-like structures like we see up here, that's when we call them a crystal lattice. So elements can come together and form two different substances, crystal lattices or molecules. Talking about elements themselves. So if a substance is made up of just one type of atom, like I said before, it's referred to as an element. Molecular elements are made up of small molecules. So carbon is a special element that we're going to talk about here. Carbon can form special large molecules called buckyballs, which is what we see here, which is 60 carbon atoms all joined together to create this buckyball shape. Now, this is really important in medicine. We can use this for drug delivery because it's hollow inside, it's just got carbon on the outside. We can actually put medicines inside the buckyball. It's really small because it's only 60 carbon molecules, 60 carbon atoms. Put something inside there and then move that into the body in like a transport system. But carbon can also form crystal lattices, which is something that normally only happens in metal elements. So carbon's really special in those aspects. Talking about, so atoms, smallest building block of everything. Elements, a group of the same atom or same type of atom coming together. Now moving into compounds. So these are molecules that consist of different types of atoms. So for example, we can see here, we've got a crystal lattice, and we've got sodium and chlorine atoms coming together. And when they come together, we have a compound, sodium chloride, which is table salt. Most compounds are going to end up being crystal lattices, but some obviously can be molecules as well. And these molecules will end up being varying in size. Just a very quick summary of everything we discussed. Atom, building block of everything. Molecule, more than one atom bonded together. Element, a molecule made up of only one type of atom. Compound, made up of different types of elements and molecules. So there, basically, in all of those 5 slides before, this is what we're summarizing. Okay? So, let's go a little bit further. What's inside of an atom? And this is not the best picture, but what's inside of atoms? So, here's a little bit of a lie. Okay. Back here, I said smallest building block of everything. But you can see on the text, I haven't actually written smallest building block of everything. And that's generally because inside atoms, there are more building blocks, I guess. But they're subatomic particles. They're smaller subatomic particles inside the atom. And all that means subatomic inside the atom particles. 3 different types of subatomic particles. So we've got protons, electrons, and neutrons. Protons, because they've got pro at the beginning, or P at the beginning, they are positively charged. Neutrons, neutral, no charge. Whereas electrons, the last one remaining, we've done positive, we've done no charge. Electrons are negatively charged. So what you end up in here is, much like in biology, we've got the centre here. It's got protons and neutrons in the centre. Now, because together they're inside the nucleus of the atom. So inside the nucleus of the atom, we have protons and neutrons. Protons, positively charged. Neutrons, neutral charge. So the nucleus overall is going to have a positive charge. And what that does is that attracts a cloud of electrons around negatively charged to make the overall atom neutral, because they have to counteract the positive nature inside. And look, there can be atoms or elements that have overall charges, and we'll talk about that a little bit later into chemistry unit, of how you can deal with those charges and how you can figure out what the charge of an atom is. But the idea is we're going to try and have it neutral. Okay, so it's equal number of electrons to protons, and then you've got the neutrons as well, have no charge. So, like we've summarised here, protons and neutrons grouped together in the centre of the atom. We call that the nucleus, like the nucleus in a cell. Electrons surround that nucleus in shells that form a cloud. Those shells are drawn to the nucleus because of the negative charge of the electrons and the positive charge of the nucleus. That charge also prevents the electrons from floating off because they're physically attracted to that positive charge. So, let's go a little bit further into the nucleus of the atom. So, we know that the number of protons, or the atomic number, of an atom determines what type of atom it will be. So it's got 1 proton, we're looking at hydrogen. It's got 2 protons, we've now got helium. And we remember last week that that's the atomic number. The total number of protons and neutrons together in the nucleus is the mass number of that element. Okay. Now, isotopes is another, it's a level higher of what we've been talking about. So, we can't, if an atom changes the number of protons, it can't stay as the same atom. So, for example, if we had hydrogen here and it gains another proton, then that's not going to still be hydrogen. It's because it's got 2 protons, it's now helium. Here, in the same situation, if we have helium and it loses a proton, then it's no longer helium, it's now hydrogen. So you can't change the number of protons an atom has without physically changing the type of atom. So we're not going to talk about that. What we can talk about is atoms changing the number of neutrons. And that won't change what atom it has, because the neutrons are not going to change the atomic number. The atomic number stays the same, but the mass number will change. And that's what we're dealing with down here with isotopes. So 2 of the same atoms, but they have different number of neutrons, hence a different mass number, and they are called isotopes. Almost every atom that we know of has at least 2 isotopes. Hydrogen, for example, has 3 isotopes. So you can see hydrogen with no neutrons, we're calling hydrogen. Hydrogen with 1 neutron, deuterium. And hydrogen with 2 neutrons, tritium. Okay, they're still all of these are still hydrogen, because they've only got 1 proton, and the atomic number stays the same. But they have a differing number of neutrons, 0, 1 to 2. Still has the same atomic number because they've got the same number of protons, but they have a different mass number. Okay, so let's look a little bit more into the electrons. The cloud of electrons around a nucleus can be 100 or 1,000 times wider than the nucleus itself, despite the fact that electrons are 1,800 times smaller than a proton or neutron. And that point there, the fact that electrons are 1,800 times smaller than a proton or neutron, is actually quite important. Because when we go back and talking about these, technically, the mass number does include electrons as well. So over here, the mass number is probably 1.00 something. Over here it's 2.00 something, over here it's 3.00 something. Okay, so the mass number is roughly representing the protons and neutrons, but because the electrons are so small, we just don't include that when we're talking about it. But the electrons are physically included in that mass number too. It's just because they're 1,800 times smaller than a proton or a neutron, that we don't classify them when we're talking about mass number itself. So if we ever ask mass number, just say protons and neutrons, but know that the electrons are actually included in that. It's just they're too small to count. But talking about this size, so the cloud of electrons 100 to 1,000 times wider than the nucleus. That means that if the nucleus of an atom was the size of a golf ball, so if we got a golf ball and we said this is the nucleus of an atom, that means the electrons that form the clouds around that nucleus are going to be roughly the size of a football stadium. So having a atom with a neutron the size of a golf ball, the actual atom's size is probably looking around the size of a football stadium. Now, if you think about this, the neutron is the golf ball with the protons and the neutrons inside, and then the electrons that are around that in the cloud are 1,800 times smaller than that golf ball, so not visible with the human eye. That means that most of the space in that physical atom that's the size of a football stadium is empty space, which is really interesting to know that there's so much empty space inside an atom. Talking about how we discovered atoms and how we found out that there was so much empty space in them, that goes down to Ernest Rutherford. Ernest Rutherford was a New Zealand scientist. He discovered that most of the atom was made up of empty space, and the nucleus only is a small portion of that atom through a very simple experiment. What he did was he grabbed helium nuclei, and he fired a beam of that helium nuclei at a thin piece of gold. As we can see here, most of the nuclei passed straight through because it was just empty space. And it's gone right through that gold, and we can actually see it on the other side, hitting the other side over here. With only a small portion being hitting the gold foil, and coming back around. Now, the foil is important because the foil does actually have pores through it. So all of that flew through, but a few small particles actually deflected across around here, while most went through. And that said to Ernest Rutherford, well, actually most of this has to be empty space because it can pass through the gold foil and there's nothing to be reflected back. Okay, this is where we're talking about the electron shells, and this will be a lot easier to do in person, and we'll go through this again next week when you're back in class. I will put another video, and it's going to be a really old video below this on how to draw atoms, and that's what I'm going to get you guys to do later on this week. Not today, but later on this week. So, talking about how electrons fill up these shells. Now, what happens is the first shell around the nucleus can hold 2 electrons. The second shell can hold 8 electrons. And the third shell can hold 18 electrons. Now, when we're going to this point, and you can see they've actually got a special layout over here. That layout's not actually correct. We'll talk about that in the other video that I put below. The atoms that we're going to talk about and the drawings that we're going to do, you're never going to go past the atomic number of 18. So you're never going to have to draw beyond that third shell, or 8 electrons in that third shell. So for our purposes, we're going to go 2, 8, 8 when we're drawing these. But know that the first shell holds 2 electrons, the second shell holds 8 electrons, the third shell holds 18 electrons. You can have a fourth shell, which can then hold 32 electrons. So every electron shell can hold more electrons. And if you think about it, that's also because the radius of those shells are also getting larger too. If you're going really close to the nucleus, of course, there's less diameter there because the nucleus is condensed into that small section. And the further you go, you've got more space, and the electrons like to fill out. If you think about why you need that more space, as you're getting larger, because electrons themselves have a negative charge. And if you have 2 electrons next to each other like this, which is why I'm telling you this is wrong, 2 electrons next to each other, they're going to repel each other. They don't want to be near each other. Okay, we'll talk about that more in the video that I'll put below this. But electrons attracted to the nucleus, they'll never fall into it. That's because they're held in place by electron shells, like we just said. Think about at the year 9 level. This is not going to, you'll expand on this much more when you get into chemistry, and this will become like a very simple thing when you get to year 11, 12 chemistry, and you get much more complicated than this. But these shells, think of them like a layers of an onion. 1, 2, 3, 4 layers of the onion. Most electron shells are empty. Largest known element has 118 electron in 6 shells. So they have 6 shells going out. The closest shell to the nucleus can hold 2 electrons, and then the information we already talked about. First shell, 2 electrons, second shell, 8 electrons, third shell, 18 electrons, fourth shell, 32 electrons, etc., etc. We're getting bigger each time. We'll go and watch that next video later on, but for now, that's the end of this PowerPoint.